Hello everybody, and welcome to this session. We appreciate we're in the slightly after lunch, so everybody gets a little bit subdued, but hopefully the sugar sleeping will pass quickly. The first of these in this session, it's a combination session. We have some network monitoring, we have some I've completely forgotten what the other word is in this. Thank you. It was Hyperscaler. It was Hyperscaler. I was worried that was the wrong word. A combination of Hyperscaler work and of network monitoring or measurement-based work. The first of those, we have Zhao Li. Zhao Li is a fourth-year student, advised by Ming Li at the University of Wisconsin-Madison. The focuses interests include load store interconnects and the analysis of host networks, memory optimizations, and a focus on the CXL.mem class of systems. Her study has been on the impact of CXL memory on host cores, cache interconnect, and so forth. For those of you, I'm sure, catching up, CXL is a alternative interconnect, perhaps posited beside PCI Express as an alternative, but it has quite different properties, including those associated with memory. I'm sure we will hear about all those things. Zhao Li's interests are hardware performance counters, exploration of memory access optimization methods that leverage the unique characteristics of CXL memory. I would and should have pointed out before she starts, I'm very sorry, our program for this session has actually changed, and one of the authors, there was a visa snafu, and one of the presenters became unavailable. So in the next paper will not be the pre-TE paper. That's actually moved to the bottom of the session. It'll be the last paper in the session, just to prepare you all for that small change. Of course, it's only minor, and you would all be here for the whole session, I am sure. Anyway, Zhao Li, thank you.
Okay. Hi everyone, I'm Zhao Li, advised by Milu at University of Wisconsin-Madison and Yubin by at Beihang University. Today, I'd like to introduce my project, PathFinder, a system tool to understand and profile CXL memory. For the first, Compute Express Link, or CXL, is a high-speed interconnect technology. It's based on memory semantics. And CXL is organized into 3 layers, built on top of the PCIe physical layer. Now, CXL supports 3 types of protocol: CXL.io, CXL cache, and CXL memory. In our work, we focus on the CXL memory, which is the basic for memory pooling. CXL memory behaves similarly to the local memory and accessed by load store instructions from the host processor. As shown in this figure, the requests from the core are first solved by the L1 cache. If they are missed, they go to the L2 cache. If the L2 cache also missed, they go to the last level cache. And when the request miss the entire hierarchy, they will go to the main memory. And in our case, it could be local memory or CXL memory. So there are 4 types of requests, same as the local memory. Will generate CXL transactions. They are demanded to read, demanded to write, read for ownership, and hardware fetch. So to make it more concrete, I will take the demanded read path as an example to describe a state path. Starting from the host core, a demanded request first solved by the L1 did cache. And if L1 cache miss, it will go to the line file buffer. The line file buffer is a hardware FIFO queue with tons of cache line entries to buffer date. If the line file buffer also miss, it will go to the L2 cache. And if the L2 miss, it will go to the last level cache. The last level cache is coupled with a caching and a home agent, or in CHA work with Snow Flitter or SF. They both work to manage Snow requests. When the demanded request meets the entire cache hierarchy, it will go to the flex bus, so the mass. The flex bus is built atop the PCIe physical layer and the connecting CXL device. When the request arrives at the CXL device, it first passes by the CXL memory controller and then finally accesses the CXL DIMMs. Unsurprisingly, the Type 3 CXL memory is actually slow. And for example, on our Sphere Rapid server with Intel Agilex card, we run the Intel MLC utility, and the local memory can achieve 103 nanosecond latency and 131 gigabits per second bandwidth. However, on our test bed, CXL memory only achieved 353 nanosecond latency latency and 70 gigabits per second bandwidth. The slow CXL memory not only slows down the application performance, but more detail, it will store the processor pipeline and changes the entire memory system behavior. Specifically, they come up with 3 issues. The first is the slow CXL memory will congest qubits architectural components such as landfill buffer, as the request must take longer time to commit than it affects the entire queue. The second, it changes application data locality and working set because the remote read and prefetch to CXL memory also takes longer time. And third, we see more CPU back pressure, so the memory parallelism is limited, and it's also cause issues. As a result, it's important for us to calculate how CXL memory flows travels different architecture in the end-to-end fashion from the core to DIMM, localize the system bottlenecks, and provide more optimization insight for the developers. However, our community lacks such a tool, so let's go with our PathFinder. And first, this is the outline of my talk, and we go to the challenge and prior work. Achieving this entails 3 challenges. First, CXL memory data paths have many stages and is not transparent across many components. Also, take the demanded read path as an example. Its origin from the core across many architectural components finally go to the off-chip. Therefore, the performance of demanded read path is dependent on a compute, memory, and I/O. Second, the load and store instructions are tightly coupled with the deep and out-order execution pipeline. The processor will issue load and store instructions at nanosecond granularity, make it hard to trace them all the requests. And third, the local and CXL memory flows share the underlying hardware. Their data paths are overlapped, making it hard to trace. And for these 3 challenges, let's see how prior solutions work and why they fall short in these 3 problems. We categorize them in 3 types. The first type is microarchitecture profilers, such as Intel V-Twin and AMD UPerf. They use performance counters to divide the CPU pipeline into many parts and find the pipeline bottleneck. They're effective on chip, but however, when we use CXL memory, they cannot link the cooling efficiency with the off-chip CXL memory. A second type is some latency bandwidth benchmarks. They test memory under different patterns and tell us what is the CXL memory performance, but they didn't tell us if there are any issues in the host, such as whether CXL memory stores the processor or whether CXL memory flows kills other local memory flows. So facing these 3 challenges, but prior solutions are inadequate. Therefore, we need a systematic and end-to-end profiling tool to understand and analyze CXL memory. Therefore, in this work, what we do is to try to dissect the CXL memory execution path, and we found we can use performance counters to do this. PMU, Performance Multi-Unit, is a specialized hardware architectural module. It can monitor processor execution, memory subsystem, the on-chip and off-chip activities, and provide programmable interface to configure events, then generate running statistics. As a result, using PMU, we are able to profile how CXL memory work. Today, processor has 3 types of PMU counters. The first type captures the processor event. The second type captures pipeline store cycles, and the third count the execution event. Now let's see how we use PMU to examine the CXL memory transactions. Let's also take a demanded read as an example. Firstly, we're looking at the core PMU. It provides a variety of counters, and we use them to capture how load and store instructions are issued from core or cache and across the core component. We use 34 counters here. And similarly, we use the same approach for the other stage A PMU, on-core PMU, and CXL PMU. These are the counters we have explored. In summary, we divide the data paths into 4 parts and use the 4 PMU for each of them to calculate their running statistics. Then we combine the result together, and we are able to know how CXL memory execution looks like. But due to the time limit, we can't report the exact profiling result. But if you are interested, you can refer to our paper to see how these counters are used. But one thing we want to emphasize is we have verified the PMU counters both in the Intel Sphere Rapids and Intel Amplify Rapids. Then we go to the PathFinder design detail. Our PathFinder is a system tool to profile CXL memory and have 3 goals. We try to make it support a variety of execution metrics and make sure it becomes lightweight. The PathFinder input have 4 entries. It includes application programs, running environment, and some user-defined profiler and report specifications. Then after the PathFinder, it generates a lot of execution characteristics, such as access intensity, data locality, latency breakdown, and hardware bottleneck, memory flows interference. And our key idea is to view the server processor and its chipset as a multi-stage closed network to identify different CXL memory data paths and apply conventional traffic analysis techniques. For example, as we show in this figure, we basically look core L1, L2, all these architectural components as individual stage. And for each stage, we capture each running statistics with PMU, and then combining all the results together, we are able to fully characterize CXL memory data paths. Since we view the system as a closed network, we can represent it with nodes and represent it as a graph with nodes and edges. The node V are architectural modules such as line file buffer, L1 date, L2, and the edge E are the links in the graph, such as mesh, flex IO bus. And also, on this graph, we define a special path from the core to DIMM as a M flow. When the application is executing, we take the snapshot of all PMU periodically. So use PMU, we build the graph, and this graph consists of a sequence of M flows, and here is the M flow figure. So based on the system model, let's see how our PathFinder works, and there are 4 steps. Now let's see these 4 steps in detail. Based on our system model, the first thing we want to do is to construct the data path map. However, the challenge to do this is the data path host is transparent. It covers many components, and all these architectural components are non-programmable, making it hard to analyze. Therefore, what we do is to walk through the PMU hierarchy in a top-down fashion, just as in the figure. Based on our PMU characterization, we are able to build the flow path map by synthesizing all the PMU counters we used. The second step, what we want to do is to attribute the CXL-induced slow cycles. The challenge is there are the CXL memory and local memory share the underlying hardware, so there are compound effects between CXL transactions and other architectural factors. To solve this, we use a backpropagation algorithm. From the CXL memory controller and DIMM, we gradually contribute the CXL memory effect back to the core. And the third step is PF analyzer. The goal here, we try to locate the bottlenecks. But due to the hardware equipment, it's also a challenge. To solve this issue, we view each architectural module as a switch and also module it as a queue. Then we use the latency from core to compute the component delay and use the path map from step 1, leverage latest law to know what exactly the queuing degree of each time flow looks like. Finally, the last step is PF materializer. It's as a single snapshot only focus on one time point. It lacks temporal information. So we employ a time serial database to save every snapshot digest. Then we take all the snapshot digests as input together to identify more execution characteristics, both in the temporal and spatial perspective. Next, we go to the evaluation part. We evaluate our PathFinder on 2 hardware test beds. The first one is a Sapphire server with Agilex-based CXL DIMMs, and the second is the Emerald Rapid server with micron CZ120 CXL DIMMs. Now let's take one case study to see how our PathFinder works. And in this use case, we also verify that PathFinder has ability to understand the quotation when there are multiple CXL sets. Looking at this figure we discussed earlier, shows the demanded read path. And in this case study, what we do is to use PathFinder to report the queuing degree when we gradually increasing CXL traffic load. And we detected the queuing happens on here. Specifically, we deploy the Redis key value store over CXL memory, and when we gradually increase the CXL traffic load using YCSB. For the reason why PathFinder is able to know the queuing degree is because PathFinder on this part uses the CHA table request a Kubernetes counter and threshold counter. The delay-based algorithm from step 3 is able to estimate what the queuing degree actually looks like. Now let's say when the traffic load is 20%, there are minimum or even no queuing happens. But when we gradually increase the concurrent CXL traffic load to 100%, the max queue length increased by 4 times. Simultaneously, we look at the flex bus latency. There's also increasing latency in this figure. And we also use PathFinder for other 6 use cases. If you're interested, you can refer to our paper for more details. Finally, the conclusion for my report. CXL is
I think that's a good slide to just leave up so people can read. I'd like us to have some time for questions. Thank you very much.
Okay.
I hope we have some questions. Are you going to leave it to me? Okay. Is there an application for PathFinder techniques in other memory systems that are complex, network memory systems, such as RDMA?
Thank you for the question. Now we focus on we use the CXL docked memory just on the host, link it directly to the host, so the PCIe bus. So I will not, for now, we not actually explore it in the RDMA scenarios.
So a thought, but not necessarily one you've explored. Questions? Anybody else? I'm going to keep the session moving along. Thank you very much once again.